So let us start talking about concurrency. And while it seems a bit not related to the previous part, which is the process management part, but what we aim is basically to establish the idea of what is the difference between a process and a thread. And this definition is widely different for different operating systems. So let's delve a bit more into what concurrency is. I mean, concurrency is when, well, you run concurrent things together and you have them running in parallel, basically. And it's extremely important for you as an operating system developer, and also for the average Joe programmer. I mean, it's not something that only operating systems people need to take care of, but it's also very important for most programmers who go beyond very basic programming tasks. And it's extremely hard to get right. I mean, it's an art, and it takes a lot of. It has a very steep learning curve to actually get right. You have probably studied quite a bit about concurrency before. I mean, or not all of you, but at least a large number of you. I mean, you have all taken the systems programming course, and that course has had a bit of concurrency, but you might have studied it also in your parallel programming course, in your multi-core course, in your matrix computation course. Yes, you might know a bit about that. What we want to emphasize here is that how concurrency is actually implemented down the hood. So, I mean, when you look at the actual operating system, at the actual kernel, how it is actually implemented, and this would help you actually to be better at concurrent programming, right? Because now you will understand, okay, this is the way it's done. And that will help you in your practical parts. So let's talk about concurrency as you know them in threads. And a thread is just an abstraction that is just like a process. And let's look at, for example, when you run Spotify and you also have 125 open Firefox tabs. A thread is basically a single execution sequence, and it's also schedulable. Let's basically talk speak about a bit about the difference between what a thread is and what a process is. And let me say that this is very operating system dependent. For most operating systems, actually a thread is a kind of a process or is a special kind of a process. So most operating systems, Linux-based operating systems, most Linux-based operating systems, they actually think of a thread as much as they think of a process, and they are just the same. And it's basically the programming model that you use to do concurrent programming, that is, use multi-threaded programming. And each thread you can think of as something that can be scheduled on its own, just like a process. And then the difference between a thread and a process in Linux, we'll talk about a bit about this in more details when we also even look at the kernel code in a later video. But the difference is that a thread to Linux is just a process that can share data with a different process, which is just a different thread basically. Okay, right? So they are just the same. They are dealt with exactly the same, and then they are just as schedulable as any process. And you can have basically protection as an orthogonal concept to this. So you can have, for example, access control on a group of threads that are basically coming from the same process or from the same parent, sort of. And the question comes is, when do you use threading? And you basically use it when the program structure requires parallelism. So you're trying to do to execute different parts or process different parts of your data in parallel. Or, for example, you have network packets arriving in parallel, or you have a server that runs basically and gets 1000 requests per second, and each request does something different, including communication with the database. So you basically have 1000 possible concurrent things happening, communicating with 1000 possible concurrent clients that are completely in different parts of the world. So this is when you start thinking, this is one of the times you start thinking about threading. Sometimes you also want to basically, or you're able to shift parts of a program to run in the background instead of having the whole program running continuously, but you might think of some parts that are, well, less important of the program. And you basically you shift these parts of the program to the background, and you do that by basically implementing them as threads, as background threads that runs in the background. And well, these can, I mean, you can prioritize threads based on how important they are in your program and so on. But I mean, you can think of them as a way to basically, okay, uh, break your code into different parts, and just say that these parts will run in the background. This is, for example, my graphics card in the this is my graphics generated for the game. Then this should be in the foreground and so on. You might also think of them when you have multi-cores. And actually, a lot of the multi-cores come with a twist. So multi-cores CPUs, for example, the Spark CPUs, the Spark multi-core CPUs, per core, they have different threads that can run per core. So you can actually run 4 threads on a single core. And that basically, if you have, means that if you have 8 cores, you can run 4 multiplied by 8 concurrent threads at the same time. But in general, in your x86 architecture, you basically have 2 cores, 4 cores, 8 cores, and then you can run 8 multiple things in parallel, and thus do 8 things in parallel for the same program. So, and that comes very handy, for example, when you talk about big data analysis, for example, I mean, which is a high port. I mean, you can run 8 different threads on 8 different cores, processing 8 different parts of the data at the same time in parallel, cutting your running time by almost 1/8 of the total time. And I mean, these are these things that multi-core programmers do. And then you have things such as I/O performance. Well, you can run a thread that basically goes and fetches from the I/O something. And I/O, for example, your hard disk, if you have an HDD, it's well, quite slow. Okay, if you talk about I/O in the terms of your keyboard, a normal human can type something like 5 characters. Not a normal human, actually, a professional typist human can type 5 characters per second. That's like, I think the record is like 6 characters per second or something. That's the maximum you can do. And that basically means that you run a few orders of magnitude, actually a few thousand times slower than your processor, because the Raspberry Pis that we are using, for example, they can have more than 4.7 billion operations in 1 second. So just that's the so you can do 5 characters, and that thing can do 4.7 billion operations in 1 second. So what you want is that you want a thread that basically runs very slowly, getting my 5 characters per second, and that's basically the slow moving, slow motion, versus other threads that basically do other stuff very fast during the remaining 4.7 billion operations, for example. I mean, of course, fetching 1 character is not one operation on a CPU, but I mean, it's like 10, even 100 operations. So I mean, 5 characters, that's 500 or 600 operations per second just for fetching from the keyboard. But then you have the remaining 4.7 billion to play with and do stuff with. So threads is a very neat way to actually do uh, sharing of resources on your computer. And as I said, threads versus processes is very operating system dependent, and sometimes even very architecture dependent, but mostly very operating system dependent. So you have different concepts like multi-threaded kernels, which are basic kernels that are able to run multiple threads and internally in the kernel itself, sharing kernel data structure, capable of using privileged instructions. So your kernel itself runs as threads. It's not your user running as threads, but your kernel itself runs as threads. You have multi-process kernel, which basically runs multiple single-threaded processes. And I mean, these are more design philosophical tags for the operating systems. How does the operating system runs internally? I mean, or what does it support? And well, multi-threaded kernels and multi-process kernels, I mean, they're also explained in much more details in the book, so you can basically refer to the nitty-gritty differences in there. But the main difference is that the first one has multiple threads sharing the kernel data structure, while the second one has multiple single-threaded processes. And then you need system calls to access the shared kernel data structures, so they don't share them directly. And then you have multiple multi-threaded user processes, each with multiple threads sharing some data, but also needing to communicate for other data that is isolated from the shared data.